All right, guys. So let's just chat about what you read. So last class, you guys basically built some stories around graphs, right? You're given a graph, and you kind of came up with a scenario that could reflect the graph, or you had to match graphs with different scenarios. So what we're going to do today is basically go through the different ways you can express a relation, right? Because there is a relationship between time versus distance, or horizontal distance versus vertical distance. So last class, as I was saying, you guys really focused on words. Do you guys agree? And graphs. So that's two ways that you can show a relation, right? So when you're relating two different things. So other ways that you can show a relationship between two quantities is, so again, we did words, okay? And you guys also did graphs. So the other ways, which you guys are familiar with as well, do you guys agree that we can write equations if we have a graph? Right? So we are focusing on linear in this chapter. So we will be building linear equations. Okay. Ordered pairs. Are you guys used to ordered pairs? If you have an equation, you can build the ordered pairs. Okay. Because you put an input in, and then what do you get? You get a output. Right? Those are ordered pairs. Technically, are ordered pairs and tables of values kind of the same thing? Yes. Right? Your ordered pairs, right, you can easily put into a table of values because your input of your ordered pair is your first column in your table of values, right? And the output in your ordered pairs are your second column in your table of values, right? So these are all different ways that you can express the same thing, right? And our kind of focus is we're going to be doing lots of equations and graphs in this chapter. Right? But again, to be able to do a graph, right, we have to be able to look at the ordered pairs or table of values. Right? Talked about this last day. Are we very clear the difference between linear and nonlinear? Right. If it's not a straight line, it's nonlinear. Simple as that. Okay. So all straight lines are considered linear relations. Okay. So what you're going to have to be able to do is I should be able to put a bunch of different relations in front of you, okay? And you will have to be able to recognize if it's a linear relation or a nonlinear relation, given any of these scenarios, okay? So I should be able to put something in words, equation, ordered pairs, table of values, or a graph. And you should be able to look at whatever I give you and tell me if it's linear or not. So that's kind of one of the first things we're going to look at today. Okay. So if you're given a table of values, right, you have to make sure you'll know that it's linear if the pattern is constant in the first column and the second column, right? So if the first column is constant, it maybe goes up by 2's, okay, and the second column maybe goes up by 5's. Right? As long as the pattern is constant, that's how you'll know if it's linear or not. So does this give you guys a good visual of that? Can you guys see how the first one's linear but the second one is not? It breaks pattern, right? It has to be constant in both. So the x's, technically it's not always going to be x, but the first column is usually your x, and your second column is usually your y, whatever variable you're dealing with, input versus output. It has to have a constant pattern. It has to go up by a constant. And I say go up. Technically, could it go down? Yes, up or down by a constant amount. The x's do not have to go up by the same amount as the y's, or down for that matter, right? But it's just the first column has to be a constant amount it goes up or down by. The second column has to be a constant amount it goes up or down by. And then if you were to plot them on a grid, they would form a beautiful straight line. If you're looking at equations, okay, we've talked about this already. If you're looking at a bunch of equations, it has to be a polynomial function, okay, first of all. And for it to be a polynomial function, you can only have whole number exponents. And for it to be linear, what whole number exponent is the highest degree of a linear? Linear is always degree 1. Good, it hasn't been that long of a weekend. right? So it has to be highest degree of 1, and it has to be a polynomial function. So if there's any weird symbols like absolute value symbols or radical symbols, you know it's not linear. No symbols, and it has to be polynomial, highest degree 1. So if that's kind of the layman's terms definition, can you guys see why the first ones are linear? Right? They follow the polynomial pattern. Okay? 2 variables, highest degree is 1. Doesn't have to be rearranged yet. You guys are used to seeing your linear as in the last one, y equals mx plus b. But in this chapter, guys, they could be written like the second one or the first one. Okay? They're all linear because, again, all the m and n, degree 1s, right? There's no weird symbols. So when I say weird symbols, guys, I mean something like this. We'll talk more about these at the 20 level, but if I gave you something like this, y equals, because you guys are used to that symbol, right? If I gave you y equals root x, do you think that's linear? No, that's what I'm talking about, a weird symbol, okay? Because technically, you guys know that this is equivalent, don't you? Is that a whole number? No, okay? So we get into a more clear definition, right? Because we deal with different polynomial functions at the 30-1 level, right? But for right now, you guys are always looking for functions, if it's linear, that could be rearranged into the y equals mx plus b, right? Or just this little x equals 7. You guys did those in grade 9, okay? X equals 7 when there's not 2 variables, right? This is just a line that goes through the x-axis at 7. So it's a vertical line. Right? So when one variable looks like it's missing, it's either going to be a vertical line or guess what the other one will be? A horizontal line. So if it was a y equals with no x, but we actually start graphing those this chapter. So if you forget all that, I will remind you as the lessons go through. Okay. All right. So so those two I showed you guys, if I gave you guys, because here we talked about table of values, how to recognize it's linear. Should I have to now explain ordered pairs? Is ordered pairs pretty much looking for the same thing? Yes. Graphs, is it a gimme if I give you a graph and ask you if it's linear or not? Yeah, that's the easiest one. If it's a straight line, yay, it's linear. Okay, if it's not a straight line, it's non-linear. So the only one I haven't talked about of the 5 here is in words. Okay, so the words, right, you have to, if it's in words, there has to be a direct relationship between something, right? So in this situation, 3 times the length of your E is equal to the length of your face. So picture writing that as an equation, right? 3 times the length of your ear. So let's do E equals the length of your face. Would that be the equation's right below, but technically would that be the equation? Is that linear? All right, it's degree 1. It's definitely linear. There's a constant variation between the length of the ear and the length of the face. You guys are used to word problems from grade 9, like Sally is having a wedding, right? She's renting the hall, right? And the hall is going to cost $500 and plus $50 per every person she invites for the dinner. Would that be linear? Yes, because there's a constant fee for the hall, right? That's not changing. And then what is changing is not changing, but is there a constant amount that is being charged per person? Yes. So those are the scenarios where you just have to read the sentence and see, is there a constant change? If there is, it's going to be linear if you graph it. If there isn't a constant change, then it will not be linear when you graph it. And you guys will see examples here coming up right away. All right, so second last thing before we get into some examples. This right here is important that you understand the difference between discrete and continuous data, okay? So when you're looking at this, a lot of times because of the word, I get why students get confused. They think continuous just means it goes on forever, okay? Technically, that's sort of right, it is, okay? But the biggest thing between discrete and continuous is what type of problem you're dealing with, okay? So that example that I just talked about, the hall, okay? With something like that, it's $50 per person, right? Do you guys remember that one $500 startup and whatever, $50 per person. That would be an example of discrete data because you cannot have person. Exactly. So you can't have half a person. So that's, if I ask you guys if something's discrete or continuous, you can't tell me unless I give you a problem behind it, like a context. So if all the points matter, right? So something like driving a car, right? And we're driving and our axis is time versus distance. Can we find the distance of the car at 1.2 hours? Yes. All the points in between the data, they don't all have to be whole numbers, right? So if all the data points matter, it's continuous, right? If you can have half a person or half a ticket, whatever the case may be, then it's discrete, okay? Does that make sense? So does it make sense they just put points there and didn't join them? Right? Because the points in between actually don't have meaning. The only time you'll join discrete data points is if you're just showing the trend, right? Just to show the trend of what's happening. But normally with discrete data, you do not join the points because it shows that all the points in between don't have meaning to the context. Guys, this doesn't really, because there's no context, the axes aren't labeled, but you need a problem behind the scenario to be able to tell me if it's continuous or discrete. Okay? And you'll see examples here soon. Next piece, this one hopefully is just review, okay, from grade 9. Which ones, if you're having an equation, I'm just going to randomly write an equation. Y equals something you're used to. Y equals 5x plus 7. Don't write any of this down. Which one is your independent variable? Which is your independent variable? Variable. We have two choices, x and y. Okay, so we didn't learn it very well in grade 9. Okay, let's talk about that. Okay, guys, think, what does the word independent start with? What's the two first letters? I-N. What variable's in the equation? The x. That's the independent variable. It's what goes in. Okay, the dependent variable is what comes out. Okay, so and why, and think about it this way too, guys. With this question, let's do context just to make it have a little bit more meaning. So let's go back to cost equals, so $25 per ticket, and we have a startup cost of say $300. Okay. If I asked you what the independent variable is, you would tell me t, okay? Because t is just representing, well, I should use it actually, and n would make more sense. Not that the variable matters, right? So n would represent number of tickets, right? So does the cost depend on how many people show up if this is a wedding scenario? Yes. So the output depends on the input, hence independent variable and dependent variable. So if you have an equation, okay, in front of you and you're asked to define your independent and dependent variable, right, you have to look at the context. Inside the function is your independent variable. The number goes in, right, normally because it depends. Your cost depends on how many people are showing up in this context. Does that make sense? Okay. So all of these definitions you'll be tested on in context, just like we'll do in the examples, right? So I'll ask you, what's the independent variable? Or I'll ask you to set up an equation and define your independent variable and your dependent variable, okay? So independent is what goes in, it's the variable inside the equation, okay? And your dependent variable is what comes out, right? Your dependent depends on what goes in. Okay. So again, in this situation here, okay, your independent is always, think if you're looking at the table of values, your independent is always your input, which is your first column. Vladimir, do you have a question? Okay. And then your output is your y, what comes out. Okay. All right, so let's take a peek. So for example, one, it says, consider each relation, determine whether the relation is linear, explain why or why not. All right, so if you look at these ordered pairs, do you actually have to look at them closely? Do you have to sort of do some math? Yeah, you kind of sort of have to do some math, because if you look at your x's, What are your x's going up by? Right, they're going up by 2. So right now it looks good for linear. Right, and there's no jump in the pattern. Because technically, guys, could I just completely take this one away? I could, but I'm not. So then this one is going up by, you guys all agree it's 5? Right, so it's going up by 5. So is it linear? So if I, again, as I was saying, if I took this ordered pair away, would it still be linear? It would be. Would it be fair for me just to take that ordered pair away and still ask you guys if that's linear? Yeah, so just remember, I could jump the pattern, but you just have to realize that if I jump the pattern, one's missing, but is it still there technically? Yes. Okay. So just be careful, not that I'm trying to trick you. I'm not going to like jump the pattern like 5 of them, but I could take one of them out, right? Because then that's not too much to fill in the middle. That makes sense? Okay. So this is definitely linear. And it's linear because there's a constant change. Right? And if you said because the x's go up by 2s and the y's go up by 5, anything like that. But the easiest one is just there's a constant change of x and y. So when B happens, you're happy because can you literally just see with your eyes? Yes. So is the second one linear? Is that graph linear? Linear or non-linear? Good, non-linear. And not a straight line. And you guys will see once we hit 30, that is an exponential function. You'll be graphing them at that level. And then, is this relation linear? Yes. Because you look, is there any weird symbols? Nope. Is it polynomial? Yes. So it is polynomial, and just picture, could you technically rearrange that for y equals mx plus b? And I'm saying x and y, but technically this would be m and n. So as long as you can visualize rearranging that, okay, in the form that you're used to, it's definitely linear. The m has a degree 1 on it, the n has a degree 1 on it, it is linear. So in this context, I chose m to be y. Technically, could you choose, because you don't know context right now, what each one is representing, could you technically rearrange it for n as well? You could. But like I said, there's no context. So then here you could rearrange it for m or n and still get it in the form of y equals mx plus b. So this is linear. And we will be doing a lot of that starting tomorrow, rearranging equations that are not rearranged for you. Maybe even today, we'll see. So you guys like using the word power. And then just so you have that example, it's those two things are the same thing. Right, so you guys go ahead, do the your turn. So you guys good with your turn? First one linear, second one not. And if you, like I said, your explanation doesn't have to be exactly like mine. Did anybody for the second one just says it's a degree 2 polynomial? Was why it's not linear? Something like that. Believe it or not, that is a circle if you graph it. That has a radius of 5. But we actually, sadly, we don't do circles anymore in high school. So that function we will never look at, but just because it's kind of cool. X squared plus y squared equals 25 is a circle with origin at 0, 0 and a radius of 5. All right, and are we good with the last one being linear? All right. So example 2 just says there's a linear relationship between the number of caribou, n, so n is going to represent number of caribou, in a herd and the number of caribou's legs, L, which relations model this relation. So we have to assume all caribou are healthy, right? So if we know that, how many legs should each caribou have? Perfect, okay? So if each caribou has 4 legs, we're going to check off, or I'm going to highlight which ones actually represent the proper thing. So would that first equation represent the equation for caribou and number of legs they have? Right? So if you're not sure, if you put 1 in there, how many legs do we have? We put a 1 in for n. 1 caribou has 4 legs. 2 caribous have 8 legs. So do you see how that formula is working? So legs should equal 4 times how many caribou you have. So this is good. All right, so do those ordered pairs make sense? Because 0 caribou should have 0 legs. 3 caribou should have 12. 8 caribou should have 15 should have 6, yeah, and then 50 should have 200. So those ordered pairs do match the equation. Right, so those are good. Does the next equation match? Because if I put 1 in there, how many legs does 1 caribou have if I put a 1 in for n? 5. Does that work? No. So this is a no-go. Legs does not equal n plus 4. Because again, if you think of your table of values, you should be able to put a 1 in and get a 4 out. You should be able to put a 2 in and get 8 out. So does this table of values make sense? No. Because right now 3 caribou have 6 legs. No, that's not good. Okay, and then our last little guy here. Is this discrete data? Absolutely. Because can you count how many legs 2.5 caribou have? No. Right? So discrete data, this has context, so we can now talk about discrete versus continuous. So this is definitely, because you can't have, like I said, a 0.3 of a caribou, right? Is it whole numbers? Yes. So it's definitely discrete data. So looking at this, 5 caribou have 20 legs. Is that okay? 10 caribou have 40. So is it looking like this is a good graph? And even though there's some, like I said, there is some data values that have meaning in between. Do you guys agree? But it has to be all data values have meaning. Because with discrete data, you're not going to plot every single point. Because is there still lots with discrete data? Yeah, there's still lots. Okay, there's still infinitely many, but not all. It has to be all. Okay, so just always go to asking yourself, can I have a point of whatever I'm dealing with? If you can have a 1.1 of it, then it's probably continuous. If you can't have 1.1 of whatever scenario, then it will be discrete. That's the easiest way to kind of picture it and look at it. So this is a good one. All right, so last question is from basically this question incorporates everything of all the definitions. So go ahead and read it, and then we will, and it is a true story. It's not a made-up one. I don't know if he's alive anymore. We'll Google that later. Probably isn't, because this came out of your textbook, and your textbooks are pretty old. All right, so example 3, we're dealing with a frog jumping contest, okay? And what's the frog's name? George's, right? So we have a frog named George's. He jumped consistently how far every single jump? 2 meters. So since he is jumping consistently, guess what that makes it? Linear, right? So if this frog jumped a little bit less every time, that's how you would know it wouldn't be linear anymore. But since he consistently jumps 2 meters every time, that's how we know it's linear. So that answers the first one. Right, so it's definitely linear because he consistently jumps 2 meters. So in your own words, doesn't have to be exactly like mine. So the next one, create a variable to represent each quantity in the relation, which is the independent variable and which is the independent variable. So this would be an example of you starting to write equations. Can you use whatever variable you want? Yeah, you just have to define it. So if every single one of you gave me 2 different letters of the alphabet on a quiz, all of it would be marked right as long as you define them properly, right? Because you can't just say I'm using M and N. What do they represent? So you guys tell me, what variables do you guys want to represent for this one? Because I don't care. Okay, J and L. Which one? J and, what did you say? L, sure. Okay, so if we use J and L, okay, what is J representing? Like jump number? Okay, so jump number. And L represents length. And let's put our units on that. So it's meters. I'm going to be a little bit more specific actually. So L is going to represent total length in meters. So create a variable, we did that. What is the independent and which is the dependent, which is the independent. So now that we labeled them, right, so J is going to represent our jump number. L is going to represent our total length in meters, which is our independent variable. J, good, the jump. Because you guys agree that we have to know what jump number we're at before we can know the length? You're right, so dependent, right, the length depends on the jump number. So we need the jump number. Before we get the length. So now I've started the table there. So where should we start? What number? To me, you should always start where, like, it's like when he hasn't moved yet, right? So where has he not moved yet? Jump number 0. Because then you have the start. Do you guys agree? So you should always want to have the start of your graph. So in context to this problem, because some of them, if it's just a random equation, you don't know where the start is. So you could start anywhere. But in this context, the frog, we want the start when he's sitting before he starts jumping, right? It would be a good place to start. Because this one does have context. So then now it really doesn't matter. So if I don't tell you what numbers to use, all of you can use different numbers. So what number, what next do you want to use? Jump number? Sure. Next one? Sure. You guys are just going to go constant? Okay. 1, 2, 3, 4? Or do you want to change it up? 1, 2. Again, does it matter? No. So if this was on your next quiz, you could pick whatever numbers you wanted. Oh, I shouldn't say any numbers you wanted. What kind of numbers do you have to pick? Whole numbers. Good. Okay. So I shouldn't say anything. So you can pick any whole numbers, and then you adjust your graph accordingly. Hence why there's no scale here, okay? Because you could use jump 50, even though he's probably done way before jump 50, but you don't know that. They didn't give you context of how many times he's jumping. Yeah.
If you have like continuous data, you still want to see numbers.
No, you don't have to. You can use whatever you want. It's just if it's continuous, it's just nicer to use whole numbers because then you're not approximating as much, right? But you don't have to. You could use any real number or any rational number. All right, so then if he jumps 0 times, what's his distance in meters? 0. If he jumps 1, it's 2, and then 4, and then 6, and then 8. So create the graph. And you know what, guys? So we did say, I'll just write it here, what are appropriate values for an independent variable? Appropriate values are whole numbers, so we might as well get that in there. Now, I didn't ask you for this, but do you think it's a fair question for me to ask you to write the equation? Absolutely. So we will start writing equations very soon, but we might as well put it here anyway. So if we use those variables, right? So we used L for the distance and J for the jump number. So if we wrote the equation, it would be? Perfect. L equals 2J. That would be the equation. Right? That's a direct variation equation, right? Because the jump number varies directly with the length. All right, so then from here, please make sure, this is where if you have to build a graph from scratch, you have to label your axes, okay, and you have to put your scale on it. That one I'm not picky with. I won't take marks off if you don't put a title on it, just because I don't care, but some teachers would care. I just want axes labeled for sure, because then that is, nope. I would like you to not really tuck it in, like make it spread out as much, but to me, guys, that's just me, what I like. Technically, if you fit all 4 into just this little piece right here, because technically, could you fit it all in right there? Do I have to mark it right? Yeah. Remember, guys, I'm that teacher that if it's equivalent and it's right, I'm marking it right. Right? Just aesthetically. So I do need the title on the axes, though. Independent goes on the horizontal axes. Yes, it does. Please make sure you do not flip your axes around. So you're independent on the horizontal axes, you're dependent on your vertical axes. Oh, am I going to run out of space? And if there's units, please make those have to be part of your title. And does your scale have to match? No. All you have to worry about for your scale is that it consistently goes up, right? Your x-axis, well, in this situation, technically it's not an x-axis anymore. What is it? It's a j-axis, and your y-axis technically isn't a y-axis anymore. It's a l-axis. So as long as your scale is consistent, right? In this situation, your j-axis, we went up by 1s. Your l-axis went up by 2s. That's fine. They don't have to both go up by 1s, whatever you choose it to go up by. Yeah. with here, because it is discrete data, was getting to that. You still need to put an arrow, but because the pattern shows you that it's discrete, so what your arrow can do is you can just put it off the last dot, because the pattern still shows you discrete, but the arrow tells you that there is data beyond. Right, so that is good. And then again, is it discrete or continuous? Discrete. And if I asked you why, will you be able to explain it? Perfect. So something along that lines, because I will ask you, discrete or continuous, explain why. So maybe start practicing your words. Explain the why there too. Whole. Exactly. So the wording of the problem makes it for sure discrete, because they're not measuring any half jumps, quarter jumps. So once he doesn't make a 2-meter jump, it's not measured anymore. He's done. All right. So guys, with that, I think we'll see how you're doing with the practice, because we do have a 45 minutes. So I think we might start the next lesson at 1/4 after, but we'll see how you guys are doing. So in your assignment booklet, go to lesson number 2, run through those problems, and then like I said, in 20-25 minutes, we might start rearranging equations.